I would be really surprised if life in the universe uses DNA, but I wouldn't be surprised if it uses carbon, because that's a more fundamental molecule that's very common. It's a lot more common in the universe than silicon. Water is likewise a very common solvent, and it has some unique properties. Water and carbon, to me, are more fundamental units than, say, DNA, which is a lot more complicated and probably wasn't even in Earth's earliest life.
Dr. soon-to-be Professor Sarah Rugheimer, welcome to the Into the Impossible podcast. How are you today?
I'm doing great. Thank you for having me.
So great to have you. I just absolutely devoured your book, audiobook, which is an Audible Exclusive. We're going to talk a lot about that. And I want to just read a brief bio. If I read the whole bio, you're so impressive, Sarah, that it will take the whole hour that you have generously and graciously allotted me. But currently, Sarah Rugheimer is an astrophysicist at Oxford, working on how to detect life on an exoplanet by looking at exoplanet atmospheric biosignatures. In 2020, she was selected as a TED Fellow, and she has a wonderful TED Talk, which has been seen by almost 1 million people in just a couple of weeks. And you can find that. It's called Searching for Microscopic Aliens. I'll put a link to that here. Maybe we'll put some highlight. They do a great job. And your wonderful audiobook is an Amazon Audible original, Searching for Extraterrestrial Life. And I wanted to start there with Amazon because, as you know, today was the first voyage of the New Shepard spacecraft, piloted by the proprietor of Amazon, Mr. Jeff Bezos, and his brother, and an astronaut named Wally Funk, who was one of the original Mercury 13, I think. And so there was life in space for a little bit today. And actually, I want to get your impression about where we should be going. If you looked at aliens looking at us, today they would have seen, 4 people heading towards them.
That's an interesting question. I kind of view them as separate and in some ways a bit contradictory. So I'm really excited about Wally Funk. She's the oldest astronaut now, 82 years old, part of the Mercury 13 program. Really excited for her to have lived out that lifelong dream. And then there's this tension, though, because we have people from the private sector who can just put whatever they want into space, say, like satellites and, is it the Starlink from Elon Musk and whatnot. And I would say there's some tension then between the scientific community and how that would influence our observations. Or what I'm worried about as an astrobiologist is I'm pro-human exploration of space. Absolutely. We're explorers. I climb mountains. I climb mountains just because they're there. I am definitely pro-human space exploration on the long term, but I'm really worried that we're going to screw up our ability to study the red planet, especially Mars, if we send humans there prematurely. So if we go there before we can actually explore it to see if there was life or if there is current life under the subsurface, if we instead contaminate it with us and all the hardy microbes we bring from Earth.
So this month, we've had on several different scientists from around the planet talking about life, entropy, the origin of life, and even the definition of life.
I go back to NASA's working definition because it is just very convenient. Of course, we don't really know because we're still hampered by the one example of life that we have on Earth, which is Earth life. So, this idea of a self-sustained chemical system capable of undergoing Darwinian evolution, there's a few very broad things I like about that definition. One of them being that it is chemical, that it can evolve, and those things I think are interesting. However, what if we come across artificial intelligence that's quote unquote past might be alive? That life would not be included under that definition.
And when we think about, as Max Tegmark calls Life 3.0 artificial intelligence, what do you make of the fact that we've been very much focused literally and figuratively, in some cases, my colleague, Professor Shelley Wright here, searching for optical signals from SETI, from Advanced Extraterrestrial Intelligence. What about this predilection that mostly SETI has been about looking for technology or technosignatures? Is that just because that you kind of look for your keys under the lamppost, as the old joke goes, or should we pay more attention to the kinds of signatures that you look on from the tiniest aliens in the universe?
Well, the short answer is we should do both. I don't think that's at odds with each other. Certainly, I think we have, if you look at the history of life on Earth, life has been on Earth basically as soon as Earth was habitable. We have signs of life dating back very far in Earth's history. And then it was single cellular for most of Earth's history. And it's really only in the last, billion years that it's been more than one-celled type of life. And then even just in the last 100 years that it's been technological, us. And so, when we think of Earth as if it is a representative planet, for most time, we would have seen the microbial biosphere. So I think that is our best chance for finding life in the universe. Sorry, not the solar system. Also in the solar system, I think we might find microbial life. But in the universe and other planets. However, we should also search for intelligent signals, because that is definitely a clearer signal. If someone waves at you and says, "Hello, we are here."
I want to first take a step back in your past world line, where you come from, where you've been. You're from Montana. You make no secret of that. You mention it with a great deal of Montana pride. I know most of what I know about Montana from the TV show Yellowstone. And I hope that's not representative. That's kind of like Sopranos move from New Jersey and go to Montana. But if you haven't seen it. But the other thing I think about Montana a lot is like looking for fossils and dinosaurs and so forth. And I want to ask, was that part of what's in your intellectual DNA, this search for ancient signals? Did that arise in part because of the unique place that you came from, Bozeman, Montana, a town of 50,000 people?
I don't think it did, though. In hindsight, one could see how you might describe that. So my dad was a physics professor at Montana State University. And in fact, he would do talks for the local museum. And then they would send us on dinosaur digs in the summer for free. Like, that was his exchange with the museum. And so, as a kid, I did go out into eastern Montana and just, try to use like little brushes and chisels to see if I could find dinosaur bones. Found a few. It was exciting. I didn't become a paleontologist, and then in the end, I didn't even want to be a physicist. So my dad was a physics professor. My brother is also a physics professor. All of his children have a degree in physics of some sort. And so I really told my dad, I was like, I'm never, ever going to take a physics class as long as I live. I hope you're okay with that. And my dad was always supportive. He was like, you got to major in what you want to major in. And so I don't know. I think I was going and thinking about robotic engineering, in my first year at a community college in Montana. And then I looked back. Well, I guess it's first before that, I didn't even want to take physics. I took accounting instead, and that was really boring in high school. Long story short, I switched out of accounting. The only class that would take me that late in the semester was physics. I loved it. And then here I am. That's the short story of it. But I realized at some point it was stupid not to go into physics just because a lot of my family had gone into physics. And I kind of rediscovered it for myself. And then I made the same sort of declarative statements against astronomy while I was in undergrad. I was like, oh no, I'm never going to become an astronomer. And here I am.
Yeah, you went from accounting. The next major alphabetically was astronomy. So here you are. So on the cover of Searching for Extraterrestrial Life in the Audible bookstore, there is a picture of an unidentified flying object, a flying saucer, shall we say. It looks to be pretty well identified, a very, very clear techno signature. In the last month alone, I've had several different guests on, from Michael Shermer to Seth Shostak. Earlier in the year, I had Jill Tarter, Sarah Seeger. What is this fascination with UFOs as alien craft? That seems to be a pretty big leap in a lot of ways. And then there are a lot of my listeners right now who are screaming at me, no, that's the most likely explanation. So we have a very erudite audience, very diverse. But tell me, what is it about this topic that immediately conjures up flying saucers, so much so that you have this very clickable, cover picture on your audiobook of a UFO, when you really spend a lot of your time looking for microscopic things?
Yeah, great question. Certainly, I have no input into what Amazon puts on the cover of these things. But when we think about these recent Pentagon videos, I watched some of your podcasts on that, some of the podcasts, for example, with Mick West, debating the origin of some of these features. And I think there's a couple things that I think capture us. So one is we really want to not be alone. And so even if we find life on another planet and it's microbial life, that to me is amazing. And that would be just the discovery of the human kind. However, we might still feel lonely. If we just find other microbes on another rock, it's not like we can really communicate with that. It's similarly, if we find even a crow or like something like a bird, we can't talk to that about our, sort of our esoteric and big questions about why are we here and how did the universe begin and all these things. We can't like test our theories against them. So I think we really want to find life that we can communicate with. And so there is this push to try to validate and believe. I would say we have this bias. It's a bias stronger than the confirmation bias. Of course, we see what we want to see. That's a very well-known bias. We really have to pay attention to that. But then there's also the bias of just believing what we want to believe to be true. And so that's also a very strong bias. And I think we see that play out in these trying to identify these aerial phenomenon, because all of them really have shown to be relatively boring Earth phenomenon. As far as we know. And I think it's also, I would just say, like we hold these unidentified objects at a higher level of evidence threshold than we do for murders. We don't solve all murders on Earth, but we expect to solve every single unknown sky. I mean, that seems a little bit ridiculous to start pinning aliens on it.
Yeah, I view that as a tribute to science and our power of science, as you point out, in the book. If you ask the average American, how much does NASA's, budget, what fraction of it of the U.S. budget, they'll say, it's 50%, 20%, and it's like less than 1%, as you accurately point out. But so it's a tribute that they think that we can answer all these questions. I always say, science means knowledge; it doesn't mean wisdom, and there's a big difference between the two. But I think part of the wisdom is knowing the impact of the science that we do. Mm-hmm. And I want to take us back to the 1990s when you describe in the book, Bill Clinton had a press conference following the discovery of possible tentative signs of microbial life on a meteorite from Mars that landed in Antarctica. And I just feel, regret that the times I've been in Antarctica, I've never picked up a meteorite, Martian or otherwise. But nevertheless, this particular artifact made headlines around the world. In fact, there's a scene in the wonderful movie Contact, based in part by one of my past guests, Anne Druyan, and her late husband, Carl Sagan, where they have, in the movie version, they have a press conference where President Clinton's talking about the discovery of these aliens that Ellie Arroway found, right? And it's so prominent in people's minds, these discoveries. First of all, I want to take two aspects of this question to you, pose two questions to you. One is, if we discover that these were definitively real microbial life forms from Mars, it seems to me the impact would be pretty short-lived, because most people don't know that they've never been confirmed or refuted, right? So as far as most of the American public knows, the same public that believes 20% of our budget goes to NASA, they probably believe that there was Martian DNA or some microbial life found, right? So 30 years later, 20 plus years later. So what do you think would be the long-term impact if we found microbes versus finding, a techno signature in terms of a spacecraft or radio signal? What's the differential impact between various gradations of life?
Yeah, I mean, it's an excellent question. It's something, as someone who really wants to find evidence of life on another planet, whether it be microbial or complex or intelligent, I'm staking my whole career on this. This is what I, gets what gets me out of bed, so to speak. And one of the sad things about this is I think that people will be underwhelmed when we actually come up with a discovery, because they're like, oh, didn't we already discover microbes on Mars? Or didn't we already discover microbes in Venus? Or didn't we already discover, wasn't it clear that those alien signals and alien UFOs are real? And so I think that people tend to already believe there is life. And so despite the fact that we have no robust evidence for life, we just don't. None of the evidence that we have really crosses that threshold to be considered robust scientifically. So then we should be excited if we do detect life, but I think a lot of people will have thought that we already detected that. And there's a couple reasons for that. Some of it's bias in media reporting, how scientists talk about things, kind of a misunderstanding of scientific evidence and the scientific process. But yeah, so I think that's one fear I have, is that when we do find evidence of life, it won't be met with the appropriate awe that it should be for being one of the most fascinating and profound discoveries we could have in our life. And then, of course, yeah, if we can actually have any sort of technological signal that we receive, that would be even more fascinating.
My thumb's rather occupied right now holding up good old Carl Sagan, but yours is free to push that like button. And don't forget to subscribe. It really helps us with the algorithm. Now back to the episode.
Right. Yeah, I always say if you want to know what it would be like right the day after the discovery is confirmed, announced, and, at the White House, just, go down to the beach and scoop up some water, and there'll be trillions of microbes in there. And pretty much people will kind of move on with their day. There are people that say this would be the most profound thing to discover microbes. I tend to think not. And the reason is, just look at the history of how awfully we treat life on Earth, both animals and humans, right? It's just human history is replete with the denigration of human life as a value. And I think that's one of the worst aspects of technology, is the cheapening of human life. But anyway, finding microbes, would be interesting, I think, to many people. But what would be the impact the next day? It's hard to say. But you did bring up something very important, which is the way that media cover things. And I always have this, probably based on my experience with Bicep 2 and other things that I talk about in my book, is this issue of, the lead story is always above the fold, like literally above the fold. New York Times, San Diego Union Tribune, Toronto Star Herald, whatever. And then the retraction, if it ever comes, is on the Saturday edition, page B17. Nobody knows about it. Nobody reads it. So I claim that scientists should keep a budget, and that some of that budget should be for PR, and some of that budget should be held in reserve as a hedge against the risk of retractions. And I think we owe it to the public to not only trumpet what we think are our theories and successes, but you brought this up, and I want to get your take on it. It's so sensational. You go through very accurately and very delightfully in the book the history of that Martian, claimed Martian find. And I didn't know half the stuff. I mean, I knew almost nothing. I just knew that it hadn't been confirmed, really, and that it was probably premature. On the other hand, you go through it meticulously. And I also remember there was an announcement of alien-type life that eats sulfur and whatever found in Mono Lake here in California. Again, these are peer-reviewed things. These aren't just like, they're just, one-off things like some scientists. They're good scientists. You go through their finding. And yet, so what do we do about that? What do we do about the kind of type 1 versus type 2 error risk to the credibility of science that tends to proliferate both in my field and in your field?
There's a number of things that we should do. And this is certainly relevant as we even go right now through our age of misinformation, alternative facts and false facts, and all of this too, because there's a flood of information on the internet, and how to tease out what is real and what's not is one hurdle. And then a separate hurdle is, even in these prominent publications, like you said, they publish the main finding, but they don't necessarily publish the alternative, updated view once the scientific community has looked at it. Because with any of these claims, I guess if for your audience, they probably know that you're going to have a huge press release, because it is an exciting discovery. It's going to be embargoed, which means a lot of scientists haven't yet been able to look at this discovery. And then once you put it out, you're going to have a whole bunch of people think about other things that you forgot to think about. And then it's going to go through that process of vetting, and maybe it'll be proved to be true, such as the pulsar planets. The very first exoplanets, we kind of forget about them. And I feel sad because they didn't win the Nobel Prize, even though they were the first exoplanets discovered. So those were eventually confirmed to be true, even though they weren't believed at the time. And then you have other things like the Martian meteorite, which hasn't proved to be true, but you don't see the same level of media attention paid to the other parts along that story. So, I think we'll get to the Venus discovery, but actually a lot of the follow-up studies on Venus have been published, and I've seen them more prominently in the news. So I'm excited about that. I think it allows the general public to see the process of science and kind of understand it a little bit more, because I don't want people to come away with thinking, we don't know how to, like, nothing's true. No study you ever read is true. Scientists don't know what they're doing. But I do want them to have, some skepticism while also having that excitement at new discoveries and retaining both of those things at the same time.
You talked earlier about, kind of a working definition of life. You didn't actually make reference to DNA or even carbon-based life. You talk in the book about these things that have a delightful name as an acronym, but are almost unpronounceable. Polyaromatic cyclic hydrocarbon, PAHs, also known as PAHs. Yeah, let's just call them PAHs. You speculate delightfully about, work that's been done, that maybe there could be some version of DNA, as Schrodinger himself thought, some crystal or something like that, later found to be not accurate, but DNA instead. But talk about that, the alternative life, not alternative facts, but alternative life modalities that don't use DNA, RNA, as you discuss in the book. You talk about the RNA world hypothesis, origin of life. Talk about alternative. That was fascinating to me. How could PAHs, PAHs be candidates for encrypting and coding genetic information?
Like any molecule that can link together and contain information. So you could think of, in DNA, we have 4 molecules. RNA also has 4 molecules. So, but you could imagine just like in computers, a 0 and a 1. That's kind of the basic level of information. And so even if you have just molecules that can link together and encode an on-off sort of switch, it would take maybe more of them to convey the same amount of information as, say, if you had 4 switches that you can relay information through, but you can imagine information being propagated. So I think when we look at various origin scenarios of life, or indeed when we're trying to find life in our solar system, this is definitely more applicable to solar system exploration than exoplanets, where we're more limited by trying to look for something we can understand. But in the solar system, we want to be relatively agnostic as to the type of biochemistry it could be. And so we want to look for any type of complex biochemistry. It could not be based in the molecules that we know. So this is, going away from PAHs, but if we look in Titan and the liquid ethane and methane lakes there, what if you had similar sorts of, like in a totally different biochemistry there than what we're used to, but if it can transmit information that and support life, then that would be fascinating. But we just don't know yet. So I think we don't yet know if the phase space of life is open. I would be really surprised if life in the universe uses DNA. I think probably not. But I wouldn't be surprised if it uses carbon, because that's a more fundamental molecule that's very common. It's a lot more common in the universe than silicon, for example. Water is likewise a very common solvent, and it has some unique properties, more common than liquid methane. So I feel like, water and carbon to me are more fundamental units than, say, DNA, which is a lot more complicated and probably wasn't even in Earth's earliest life, where you maybe had RNA or precursors to DNA like PNA or TNA or other information carrying systems.
So when we think about, the sort of propensity to be biased and prejudiced as scientists, not just the invidious prejudice of sexism and racism that does still persist in some corners of academia and science and astronomy itself. And you're a fierce advocate for women in STEM. You also have the honor of holding the Caroline Herschel. She is one of the most titanic astronomers of any gender in human history. And here at UC San Diego, we had Margaret Burbidge, who also was, I believe, overshadowed for a Nobel Prize in favor of Willie Fowler and other people. And she, of course, made the fundamental contribution to the observations that led to our model of stellar nucleosynthesis beyond, sort of the lightest elements on the periodic table. But when we think about looking elsewhere and kind of the bias that we have towards what looks like us, as I say, not just in terms of our sociology, but in terms of what life could be. Could phosphine potentially fall into that? Because the paper and so forth, the work by Professor Jane Greaves and Cardiff and her collaborators Sarah Seeger and Carl and others at MIT, they are sort of looking where the light is. In other words, they know that phosphine was a biosignatures of life on Earth. And so why not look elsewhere? So what is that? What is that, the danger of these different biases? Confirmation bias, look elsewhere effect, the file drawer effect, that we suffer from as astronomers, as physicists.
Absolutely. I mean, first I would say is in some ways we are, for exoplanets, again, not for our solar system, we are necessarily hamstrung to look for things that we can recognize. So it could be that life exists in the clouds of Jupiter, for example, but if we can't tell if that's true in our own solar system and we've taken high resolution images of Jupiter with Juno, how are we going to see on an exoplanet? We just can't even really comprehend what that biosignature would be. Or similarly, there very well might be life under the ice cap, the ice ocean on Europa, yet that doesn't have an atmosphere, and so as an exoplanet, it's relatively useless to us. So I think we need to look first for global biospheres that we could detect. And so I think this is a really common misconception, actually, in the public as well as within the scientific community, is when we say habitable planets, it's kind of a short term for something that we could detect from light years away. It doesn't mean that that's the only place that life could exist. And we know that, life could exist in many other places within our own solar system. But it's just saying, where could we actually have a hope to detect this from light years away? Now, all bets are off when we look at our own solar system because we can actually go there. We can send landers, we can send rovers, we can look for this other type of life. And so I think that's where we should really test out some of these alternative biochemistries. Venus is a great place to look if such weird life exists. Same with Titan, same with Mars, Europa, all of these other places. We should look there because alternative biochemistries are kind of, if we can't prove them sort of in situ here in Earth or on planets around us, it's going to be really hard to detect them on another planet. And maybe we'll eventually get there. And I think we should keep our mind open. So I really appreciate the work of Sarah Seeger and other colleagues who are trying to be more open to any type of molecule we can find. But Clara Sousa Silva, who came up with the lines for phosphine, for example, she's trying to go through and create spectra for more of these molecules, but we don't even have the spectra to detect them. Right now, there's 16,000 molecules that Earth life could produce, and we only have spectra of even poor quality for 0.04% of them. So in some ways, we only are looking for phosphine because Dr. Clara Sousa Silva made the lines for phosphine, for example, and then we could suddenly look for it. We couldn't look for other molecules that we don't have the lines for. And when you look at the number of high-resolution line lists that exist, there's just not that many yet. So this is part of the fundamental science that needs to be done for us to even detect these molecules in other planet atmospheres or in the solar system.
Let's go deep into what you actually do, because my audience is the brightest in the known multiverse. And just a reminder, we're talking to Dr. Sarah Rugheimer, who's got a list of awards that would take me 2 or 3 podcasts to note. Someday I'd love to talk to you about the awards that you won for public understanding and for leadership, the Rosalind Franklin Lectureship Prize in 2019. That was the same one that my kid's favorite astronomer named Brian Cox, he won. You won, these phenomenal accolades. But tell me what they're for. Is it just for, doing something cool? What do you do on a daily basis? Do you use a telescope? Are you looking at spectrographs? Are you doing calibration? Are you building? What are you doing? And how can other people expect to follow in your footsteps? How would they go about following in your footsteps or doing the type of day-to-day work that you do?
So what I do is theory. So there are people who are interested in observations, say finding observations of these exoplanets, and I am also excited about that. However, we are not yet to the point of being able to detect biosignatures. And what really gripped my interest as a scientist is, could we detect life on another planet? And when I entered grad school, the answer was, this detection is really decades away. And even still, we're just approaching the technological horizon where we might be able to see the atmospheres of 3 habitable exoplanets with JWST. So we're really just pushing that observational threshold. And so what I do is theory to try to understand, how can we be sure of the detection? How can we think of false positive mechanisms? How clear would the signal be? Would it overlap with other features? What kind of resolution do you need? How big of a telescope do you need? So that we can create future missions, these kind of horizon missions beyond JWST, that are really tailored for making these measurements. So as part of that, I'm part of this life mission concept in Europe called Large Interferometer for Exoplanets. LIFE, life. And this would be something that could actually detect hundreds, or maybe we're hoping for like 30 to 50, maybe 100 Earth-like planets and characterize their atmospheres. And it's also in the infrared where more of these molecules absorb. So I'm interested in both pushing forward this sort of mission concept, which I'm a part of the team for. But then on my research side, I look at how does the star influence our observations? How does stellar activity influence our observations? So I do more theoretical computational modeling that hopefully will feed into and make our telescopes more robust for what we want to detect.
If you haven't read Andy Weir's most recent book, Project Hail Mary, you will love it. Yeah, it's actually, and you could get it like your book. Audible is actually better than any other way to get it because it's actually acted out by a phenomenal actor with sound effects, etc. Andy Weir, I'll put a link to the episode that he was on the Into the Impossible podcast. I thank him for going very deep, and we even got into like mental health issues and
I watched that one.
Yeah, why he dropped out of UC San Diego without a degree, and he went on to some success, I guess you could say. But he talks about obviously he's most well known for The Martian for now, although I think this is even a better book. But when we think about these places that people tend to look for life, it's typically been Mars. And so lately, I want to ask you about two items in the news in your cricket pitch. I don't know. We'd say ballpark when you're back in the U.S., but cricket pitch. I don't know. But anyway, the point is, there's been a lot of interest in extraterrestrial, findings, including on Venus and on potentially on Venus and potentially from this technosignature that your former, Harvard mate, Avi Loeb, talks about in Oumuamua as a technosignature in his new book that we also did an interview with not too long ago. So I want to ask you, first of all, what is your opinion of Oumuamua and as a technosignature? Do you agree with Avi and his 80 papers on the subject? It's not like he just wrote one paper and then he wrote a book and went on Joe Rogan's show and then afterwards he worked his way up to the Into the Impossible podcast. But tell me, what is, as a professional, what do you make of this?
Right. So for Oumuamua, I haven't followed all of the recent articles that have been written on alternative explanations. I'll be honest. I know that many papers have been published that are more critical of the finding. And I think more importantly is there is this phenomenon when we have low resolution data. What is it called? Is it like the Cornelia effect or something like this? We could figure it out. But basically when there's this famous crater on Mars, and it looks like a happy face. And then when you get a better image of it, the happy face disappears. And humans do this all the time. We see things when we have low resolution data, and the data for Oumuamua is just low resolution. It's just the error bars are high. It only had one pass. We just couldn't get enough information for it. So while I agree with Avi that we should look for more of these, and definitely we should spend some of our astronomical budget looking for more of these, because if he's correct in the number of these, then we should see more of them. And we should be able to do better follow-up observations on them with more time and actually see what they are. I disagree that it's a strong evidence of life. I think it's more likely to be some of these other explanations that, and it's kind of like looking with the lamppost under the lamppost. I think, like all scientists, we can fall prey to our favorite hypothesis and then kind of discount evidence that believes that. So my personal scientific view on that is that there's enough kind of holes in that theory to not claim aliens. It doesn't reach the robustness of, say, aliens. And then I would say the same is true for Venus. So we don't even think it might be phosphine. Maybe it is. It's like these papers are still coming out back and forth, and the teams are, analyzing data. New teams are reanalyzing it and saying, no, it's SO2. And then people are like, no, but you have an error in your pipeline. And so you have this back and forth, which is why science is awesome, because it is prone to falsification. You have to repeat the experiment. And I think that if we do find, first off, we'll have to see if it is phosphine. It looks less and less likely it is phosphine. There was a recent paper that shows that water activity in those clouds is very low. And water activity basically means, could life do the chemistry with water is there enough water there for it to be functional? And it's 100 times lower than any known extremophile life that we know on Earth. So there's a number of kind of holes that are getting poked into the Venus hypothesis, or even just if it is phosphine, maybe it's coming from a different part of the atmosphere. All of these things matter. And so to me, it's kind of like looking at these UFO videos. You can't just look at something fuzzy and be like, oh, that looks like a UFO. You have to get the follow-up data. Or if it is a UFO, you don't necessarily claim aliens. I mean, I've seen some weird night sky lights, and then in the end, it just happened to be that it was a military plane taking off near me, and it flew over eventually, and I was like, oh, it's a plane. But from a distance, it was doing all sorts of weird, geometrical right angle stuff. And if I, if I wasn't being skeptical, I might have claimed that I was seeing something odd. And so I think the criteria, the same old, the age-old expression that Carl Sagan popularized, extraordinary claims require extraordinary evidence. And none of these so far have met that hurdle.
Yeah, I always say, and you reference Michael Shermer in the book, and he's been on the show many times, a good friend of mine. And yeah, this kind of believing brain phenomenon that you fill in gaps when there is this noise and very low signal to noise environment where there's very high stakes. It's one thing if you're looking for a seagull, or as you talk about looking for a fly in front of a spotlight, it's not going to probably kill you. You might not be able to see it, but if you see it, if it's a bat, I encountered a bat the other day and really freaked out my kids and my wife. But anyway, I was kind of intrigued by it because they're so interesting, these flying rats, and you don't see them so much in California. But anyway, But yeah, there's a much bigger consequence, I suppose, for that to happen. But I wanted to bring up this recent, very provocative, tweet, and of course Sabina Hassenfelder, who's a good friend of many time guest on the show. She tweeted out, with almost a sense of glee, that the Max Planck Institute in Germany for solar system research in Göttingen tweeted out, phosphine in Venus's clouds, no trace. It's pretty rare. Even with the Bicep 2 affair, you might be familiar, might not be, but for my listeners, we didn't make a blunder. We didn't leave the lens cap on, or somebody had a smut. We detected extremely high levels of signal to noise of B mode polarization. And no one's disagreeing with that. It's just how we attributed it. What was the source of it? This is now saying it seems to be quite different. It seems to be saying more in the camp of almost like the opera faster than light neutrinos or something. There's actually something wrong with the original analysis. These people are so erudite. I'm going to have Jane on. I hope Professor Greaves on, maybe Sarah Siga back for a part 2 or something as well. What do you make of this? It's pretty astounding to see this huge basic flip-flop from, scientific community, we need more data, to now we don't need any more data. And we probably should focus more effort on, other planets, go back to Mars, as our focus. So what do you think of it? This extreme 180-degree flip in the scientific community, not in the public.
For any of these claims that are extraordinary, you will get people trying different explanations and trying to redo the data, and that's what you want. I think you have the same sort of sensationalized journal article titles after the Allen Hills meteorite claim as well, and after some of these other controversies. I think one of them was Tempest in a Teapot. So scientists can come up with very sensational headlines on our own without the media. But I think no matter what, Venus is a story that we should pay attention to, because it's certainly a humbling lesson as we think about exoplanets, just given the amount of back and forth on this detection. Exoplanets are much further away. Venus is next door. If we have trouble understanding it, how are we going to understand these planets orbiting distant stars? But then also, I would be curious to see what Jane has to say, as well as I'd recommend inviting Dr. Clara Sousa Silva, who is the theorist and who's the main person who came up with phosphine as a biosignature from her PhD work. So, because there are different ways and polynomial fits to this data, and depending on your assumptions, you can get different results. And so I think that we have to see how this plays out. We know one thing is that the Greaves team has taken their abundance estimate down a notch from the 20 parts per billion to I think 1 part per billion. So we'll just have to see, but they still think they're seeing phosphine. And so, it's going to go back and forth. And whether or not it's phosphine or SO2 is interesting. And if it is, even if it's a little bit of phosphine, that is unusual. And that would indicate some atmospheric chemistry that we're not really understanding, or some geological process we're not understanding, because I don't think it's life. Venus is a very hellish world. Like, just complex chemistry is going to have a hard time surviving there. So then the question is, what is it? If it is just SO2, I still think we should go back to Venus, because we don't understand Venus. Just as a kind of a side note to this, Colin Wilson here at Oxford said that at a conference, a Venus conference, they had 8 groups take the same boundary conditions in their climate models for Venus, and with 8 different climate models, and every group had a different atmosphere for Venus come out. So we just can't model Venus's atmosphere very well yet. We don't understand the dynamics. We don't understand these more thicker atmospheres yet very well, and we're going to need to as we start looking for exoplanets. So I think Venus is interesting for us on our way to understanding other planets, no matter what the story ends up being.
A lot of the book's most juicy and delightful passages that you wrote, and again, I'm talking with Dr. soon-to-be Professor Sarah Rugheimer about her research and her wonderful book, Searching for Extraterrestrial Life, Audible Exclusive, and you'll see a review there among 70 other reviews from yours truly, with an asterism of 5 stars. We are celebrating the 60th anniversary of the Drake equation this year in 2021. And I tried to get Frank Drake on. He's pushing 90. He had such a polite, declining rejection, I should say, of my invitation. It was so polite, so classy. I love him so much. But I'm not a huge fan of his equation for the following reason that you actually point out in your wonderful audiobook, which is that, we present the Drake equation in a way that if one of our undergraduates, my undergraduates, your future undergraduates, if they were ever to submit a result and it had no error analysis associated with it, we would give it back to them with an F, right? But the Drake equation is always presented as if, it's just an equation, it out pops a number, and then you just go on. But you point out, as in the book, as I pointed out, I gave a talk at the SETI Institute, that we have to do error analysis, and that's the hard part of being a scientist, right? You talked about the phosphine life a minute ago. So, but talk about that, the lack of kind of attention that's paid to the real meat of what you and I do, which is really in the details of how we look at what, as you described, systematic errors in particular, and statistical errors. So, first of all, what's a systematic error? And how can it plague results such as, estimates based on the Drake equation?
With the Drake equation, just in general, when we think about the errors, we really only know the first few terms with any sort of certainty. And then we're so limited in our understanding of Earth-type life. In fact, the equation itself is very astronomy focused. If a biologist were writing this equation, it would probably be different, and they might think of different steps that would be more interesting to put in the equation. So we could just be wrong in where we're looking for life. We could have, this bias of G stars, for example. We're around a sun-like star, but most of the stars in the universe are M stars. Is that a statistical fluke that we just happen to be around a star type that's only 6% of the stars? Or is there something there? Is it that M stars have these cooler red stars have some intrinsic flaw as habitable planet hosts? So we don't know a lot of these things. And until we get more observations of planets, it's kind of like it seems to me beyond my imaginative scientific horizon to be able to pin down the terms of the Drake equation, because especially like the last term, the lifetime of an intelligent civilization. I mean, you could put whatever number you want in there. How are we going to have some statistical answer? Unless we meet a being that has traveled the full universe, maybe even the multiverse, and we can say, give us the answers to this equation, I don't think we're going to be able to come up with that for the foreseeable future. But it's still interesting. I think it's interesting as a concept. It's interesting as how do we try to narrow down with astronomers love back of the order calculations? Could we do something useful from that? And I guess it's these same sorts of back of the envelope calculations that turned me away from astronomy when I was a physics undergraduate student, I'm like, they don't know anything to within like factors of, 100 or more. and so, but at the same time now as an astronomer, I do see some use for it. It's just not I think what people might think, we can say that there must be millions of intelligent civilizations in the galaxy. No, we have no idea because we have no idea how common life is, how common complex life is, how common intelligent life is, technological life, and how long it lasts. I mean, we just have no idea.
Yeah. And I do want to conclude with sort of a statement that I think, your job is made harder in many ways by the media as, kind of this machine. But sometimes it's even our professional colleagues who also take a liberty and make posters of Glies or Glisa or whatever, however you pronounce it. You talk about in the book, these posters, they're very whimsical. But then, people start to think, well, like, that looks really, photorealistic. Is that a real picture of the planet? And my colleague, Adam Burgasser, who I'm sure you know here, and he worked on the TRAPPIST results. And, you get these posters outside their office. I'm like, yeah, that might be kind of cool to take a vacation there. But I think it does make things pretty hard, especially when you realize that there are so, few pieces of tangible physical evidence. And when we get a little bit, we just pour over it. And I want to ask you about kind of the answer to the ultimate mystery in all of your field, which is the Fermi paradox. Where is everybody? But to hear Sarah's answers, you're going to have to subscribe to her podcast and my podcast, and I'm going to send out your answers to these questions and more to my mailing list. So you have to subscribe to briankeating.com, my mailing list. You'll get the answers to the thrilling 3 questions in which I'm going to ask Sarah about her answer to the Fermi paradox. And also, you can get it by subscribing to her podcast and leaving a review wherever podcasts are sold. And that is called Self-Care with Doctors, Sarah, because you do that with your friend, Sarah B. Remind me Sarah's last name again. I keep forgetting.
Sarah Ballard, Professor Sarah Ballard.
She's yes.
She's at Florida.
Yes, yeah. I want to have her on too.
She's coming to the UK in a week, so we could do, double Sarah's while she's here for 2 weeks.
So for now, if you want to hear the answers to the thrilling 3 final questions, including where is everybody in the universe, you're going to have to subscribe to Dr. Sarah's podcast, plural Professors Now Sarah podcast, and subscribe to briankeating.com, my mailing list. So for now, thank you for joining us, going into the impossible with Professor Sarah Rugheimer. Thank you, Sarah.